Hello Physics C world! This video is more so meant for people in my Physics C class who just went through this FRQ, but I figured this could help more people than I think. We're looking at the 2008 third FRQ, which really puts emphasis on elastic energy. Whatever, you get the gist. I will let you read this problem out yourself. Please, by all means, try it out for yourself if you have not already, and if you have not already suffered through it. I would say there shouldn't be that much to suffer with. There is not something horrible going on here, but there is always a stretch of the mind. Anyway, let's get into it. Part A. Data, plot a graph of weight versus length on axis below. Is just putting in this into here. So thankfully we don't have to do too much thinking. 0.6, 0, 0.97, almost 1, 10, 1.24, almost 1.25, 15, 1.37, almost 1.4, 20, 1.64, almost 1.6, 25. And we gotta sketch that best line of fit. And it's straight. Doom, do. Kind of like this, you could argue. Just make sure that these points from the data are specifically labeled, so that way it doesn't look like you just drew a line on there. Now back to regular blue. These are the best line you sketched in part A to determine the experimental value for the spring constant K of the cord. We're looking at a force and we're looking at a length. In this type of graph, your slope will be your spring constant, but if you want an equation to explain why, this might look a little familiar. This is force, spring constant, displacement. Displacement is not cord length or length of spring. So we would want to perhaps start from here and take slope from this 0.6 line over to this 1.6 line. And we can actually just look at it at the table here. 0.60, 1.64, that's about 25. You can say K is comfortably 25 newtons per meter. You can use your line of best fit. You would just need an answer close to 25 newtons per meter. Student now attaches an object of unknown mass m to the cord and holds the object adjacent to the point at which the top of the cord is tied to the rod. When the object is released from rest, it falls 1.5 meters before stopping and turning around. Assume that air resistance is negligible. Calculate the value of the unknown mass m of the object. So, we have an object starting up here. And, of course, just imagine the cord. It falls down 1.5 meters until its velocity 0. And now, let me make my m's clearer. Sorry, guys. And now it's at the very bottom, where it'll turn back around. If we were to write an energy equation for this, our initial energy is purely just gravitational potential energy, and as the mass moves down, it has kinetic energy, and the cord stretches, past the 0.60 threshold, turning it into elastic potential energy. So we don't have any non-conservative forces at play. We're ignoring air resistance. So our initial energy is equal to our final energy, meaning that our gravitational potential energy is equal to our kinetic energy plus our elastic potential energy. If you were to try and use mg equals kx right here, you'd find when the acceleration of the block is 0, but it's still moving downward because initially your mg overpowers the spring force, the restorative force, until a certain point. Because as displacement gets larger and larger, the spring force increases up until that 1.5 meter length point. In which case velocity will start slowing down, and go down at a lower speed until it reaches 0. So we can't quite use this quite yet. Which is why we have all of this. At the very bottom, there is no velocity, so we can cross that out. Leaving us with just this. All we have to do now is plug in. Oh, shoot. Sorry about that, guys. Isolate for M. Let's make this a little thicker. So we have M is equal to 1/2 kx squared divided by GH, which equals 1/2 our displacement from 1.5 meters. 5 minus 0.6. Recall that from this part here, where 1.5 is 0.9 away from 0.6 squared times our k constant that we found earlier. Over GH. For our class, we use G equals 10 meters per second squared. I don't know about you guys, but that just feels a little simpler. And H, our total 1.5 distance. Total 1.5 meter distance. And this should get you 0.675 kilograms for the ball. Calculate how far down the object has fallen at the moment it attains its maximum speed. Okay, this is going to go back to that explanation with mg is equal to kx again. This is when we achieve 0 acceleration, which means that our mass has been going down and down and down and down and down, accelerating until it hits 0, and then accelerating backwards up, meaning it's still going down up until a certain point where we'll go back up. We'll need this equation, and since we're looking at how far down the object has fallen, we're going to want to look at displacement. If we move some stuff around, x equals mg over k, which should give us 0.675 over 25 times 10. If I recall correctly, this should equal 0.27. However, this is our displacement. This is not the full length of how far the box has fallen, how far the mass has fallen. Remember that the core takes 0.6 meters before it actually starts being displaced. So, the full height would be 0.87 meters. I'll write out a formal enough answer for part 2. This is the full answer that I believe I wrote for DII. This first bit, I would argue, is the most important part. The rest after that is just a slightly deeper explanation of it. Of course, any phrasings near this should be good enough to get you the point. Let's just drag this down for simplicity's sake. For part 3, calculate the maximum speed of the object. So we know that we will have the maximum speed when we have mg equal to kx. But for our equation with speed in it, we will need to refer back to this. Back to our gravitational potential energy being equivalent to our kinetic energy. Being equivalent to our kinetic energy plus our elastic potential energy. Because once it hits that 0.6 meter mark, some of it will be transferred into elastic potential energy and kinetic energy at the same time. It's only after we start accelerating back up when we convert some of this kinetic energy into elastic potential energy as well. So if we want to isolate for velocity, let's move this over to the other side. Multiply everything by 2. Divide everything by m. And then take the square root. Leaving us with this honestly very massive equation. But in the end, if you plug everything back in, you should get around 3.83 meters per second. Of course, recall that our mass is 0.675 kilograms, g 10 meters per second squared, h 0.87 meters, k 25 newtons per meter, x 0.27, and just remember to divide everything by mass. And that is it. Hopefully this gave a student's perspective on the equations needed for this FRQ. But if not, there's the comment section, there's my phone number if you have it. I am willing to answer anything related to this. I just think this question was overhyped in terms of difficulty. But of course, you need to really stretch the mind, and you need to look past. You really need to look past mg equals kx for C and onward. So yeah, that is it. I will leave my answer to this in the comment section, but any suggestions, any critiques, please leave them. This is meant for you and for you to improve. I hope you liked it.